So we'll go ahead and start our discussion for static random access memory in more detail. By detail, what I mean is we will look at individually. First, the structure, how the cell structure looks like, what are the device physics for storage, and then we'll go one by one about write operation, read operation, and hold operation. Okay, that's also important because you write something, you read something, but you need to hold the data also, right? Because during hold period, if there is some bit flip, so then it will be problem later, right? Or also, as we know, these days CMOS is quite leaky. Even if you're holding data, not doing anything, there will be a lot of leakage going on. So what you can do to minimize that? How will optimize hold? Because it's not a non-volatile memory, you cannot turn it off. The moment you turn it off, things will be gone. So we'll see some of those things. One option is you can operate the memory at a much lower voltage when it is just holding data. You don't need, say, 1 volt. You can operate it at half a volt, right? So that's an important criteria. What should be the minimal voltage? Because each of those things has implication on energy consumption and the reliability. Okay, so we will see all of these as we go forward. You can ask me questions at any time. Right, so this is where we stopped in the last class, right? We talked about 2D architecture, where you have certain address lines selecting the row, right? Memory is organized in a 2-dimensional block. You can think like this. In some cases, it is called sectors. In some cases, it is called block. Doesn't really matter. Your cell, individual cell is this yellow dot that you are seeing. It is defined by the which row it is, and inside that row which word it is, right? So it requires both row address as well as column address. You need certain pins for column decoder, certain pins for row decoder, and then your sense amplifier circuitry will sense the value in that word and all, okay? Now this is the structure of a 6 transistor SRAM cell. This is a classic structure. Here there are two, first of all, you need to note down these metal lines. This is the word line, right? Which will connect entire row of memory. So all the cells that are in a given row, they share the same word line. It's a metal word line. It will pass the voltage over there. And then there are bit lines. Okay, so bit lines are more like the data that will get out, right? And so sense bit lines are connected to the sense amplifier. Word line is just to activate. Okay, I want to read this cell, so I will activate this to access transistor. So these two transistors and most transistors are more like an access, right? I want to know, is Q equal to 1 or Q bar equal to 1, right? So the state of the memory cell is stored in the voltage of the node Q, right? So if Q is 1, 1 means high voltage, Q bar has to be low because this is an inverter structure. This is one CMOS inverter, this is another CMOS inverter, this P1 N1, and they form this back-to-back latch, right? So for example, say let's assume this Q is 1, okay? Now, if Q equal to 1, which transistors will be on? Which transistors will be off? So Q equal to 1 means Q is high voltage, right? Suppose these two NMOSes are turned off. Now this is the cell which is storing data. Question to you is, if Q equal to 1, right? Which transistors are on, which transistors are off? There are 4 transistors you can see. 2 NMOS, N1 and N2, and 2 PMOS, P1 and P2. Questions to you, if Q equal to 1, which transistors are turned on? So if Q equal to 1, so N1 is not turned on, N1 is turned off, because this Q equal to 1, high voltage will turn N2 on, right? So N1 is off, okay? Because Q bar is 0. If Q equal to 1, that means Q bar is 0. If Q bar is 0, this is turn off this NMOS and N1 because N1 is connected to Q bar. So for NMOS we understood, right? If Q equal to 1, this N2 is on, and that's how it will discharge this node Q bar. How about PMOS? Which PMOS is on? P1. Yeah, P1 is on. So what is the purpose of this P1? Purpose of this P1 is to keep Q at high voltage, because this N1, even though it is turned off, we talked about leakage, right? These days in a lower technology node, transistors are always leaky. So even though this N1 is off, this will try to still discharge it through leakage. If there was no P1, after some time Q would have been gone to zero, discharged to zero through this leakage current. But because of this N1 and P1 combination, even if Q lose some charge, P1 immediately charges on because P1 is turned on. So that's why it's called static RAM. It has high stability. No matter what, it doesn't lose data as long as there is some voltage. You don't need to refresh it. It's static. Makes sense to all of you? Static means you don't need to refresh. For example, in DRAM, when you talk about in the couple of lectures later, you will see that after some time, you know, this node Q or this Q you can think about is a capacitive node that will discharge through leakage. So leakage will decide how quickly you need to refresh those cells. But here, leakage matters, but not in a big way. It's a static RAM. As long as power is there, you will hold data. So that's one important thing. You can think about this structure as this kind of back-to-back CMOS inverter, because this back-to-back inverter has a lot of interesting properties. One is, it is very stable, right? It's positive feedback. One inverter wants to, so if this is 1, this will be 0, and this 0, this inverter wants to keep it 1. So you can think about like this, it is a positive feedback. In many cases, it can be also used as an amplifier, because little bit change, this will amplify it either to 1 or 0, right? Suppose there is a little bit change between Q and Q bar, that will be immediately amplified. So many sense amplifiers and all are designed using this back-to-back inverter configuration as well. But yes, today our topic is how this SRAM cell you will write, how you will read, and how we will keep in a hold condition so that you don't dissipate too much power. Okay, so that's the topic. So now let's look at this positive feedback a little bit. So this is the same back-to-back inverter. I just pull them out. So this is VI1. So many times people will show you this butterfly diagram. So that diagram tells you how stable or how good this SRAM cell is. And this butterfly diagram is nothing but two inverters characteristics. So this is first inverter, VI1 is in the x-axis and VO1 in the y-axis. That is the inverter characteristics. If input is high, output will go to down. Right? That's very fundamental inverter characteristics. If you look at the second inverter, its input is output of this first one, right? So VI2, or in other words, this VI2 is now in y-axis because I want to keep the y-axis same, right? Because output here is the input of this inverter. So that's why I rotated the IV curve by 90 degrees. Okay, so now this is your output of inverter 2. If input is low, output will be high. If input is high, output will be low. Right? And then you combine them together because y-axis is same. That's why you can combine them together, and that's how we form this butterfly diagram or eye diagram. This is a very famous plot to characterize SRAM. Right? Very quickly, by looking at this diagram, you can say, is it a good SRAM or bad SRAM? For good SRAM, you need more spacing in the eye. Eye should be big eyes. Then it is having large noise margin. And why it is so? Because, as I said, right, there is a possibility that you can be stuck at C. So this C is a common point for both the inverter. You see? So if you are, say, C can be, say, it's called metastable point, can be 0.5. So 0.5, 0.5, 0.5, everywhere 0.5. That's a unique, very metastable point, right? So now little bit change here. You say you go from C to, say, this delta change. You go here and then you go there, you go there, you go there. Because in this curve, right, butterfly diagram, only points where only valid points are these 3 points. One is this A, another is a B, another is a C. because these two curves has to intersect. Otherwise, there is no solution, right? Because these are the same device, and this is the back-to-back inverter. So you will be either A, where one inverter, so A's output is 1, this point is 1, this point is 0, right? So output is 0. So this is a stable point. So B is also another stable point. And this C is another metastable point, because little bit change here, you will go like this. You'll go back, means back and forth like this. You'll come here, it will go like this. This inverter will make it here, and this inverter will put it here. But here, if you go little bit change, you still come back here at A. If there is little bit change in B, you will still come back to B. That's why these are stable points, A and B, which are corresponds to storing 0 or 1, right? For example, A can be Q equal to 1, which is this state of the memory cell is 1, and B is storing 0, or state of the memory cell is 0. So that's where most likely you will be. This is a metastable point, you will never be there, you will never, so any thermal noise will push it either to A or B. Now, when you power it up, right, first time you turn it on, that time what happens? So that time, what are the Q and Q bar? When you turn on the transistor, right, what do you think? Will you be at A, will you be at B, or, yes?
It depends on the process fabrication, which transistors are stronger.
Yeah, that's the correct answer. So think like this, when power is 0, both Q and Q bar is 0. Because that time there is no inverter, right, when power is 0. Now we turn on the power, so it will take some time. So during that time, you may be at C for some very little moment, right, at the beginning. But whichever inverter is stronger, that will push it to either A or B. So this little mismatch between these two inverters, which can come from process variation, even though you want to make both the inverter identical, but there is nothing called identical, right? In real fabricated chips, there will be always variation. So that variation will decide when you power it up, will you end up in A or will you end up in B? And that's a very repeatable process. Every time you power it up, you will be always ending up in A or always ending up to B, depending on which cell you are talking about. Right? So that's one interesting property, and there are a lot of research goes on understanding this property and using it for some security or some other functions. Okay. Now, this is the structure. So here, the access transistors facilitate this read and write. So you need to turn them on, right, whenever you want to read or write the memory cell, because you have to access, right? Whenever you want to read, so these bit lines are the sense amplifier connection, right? So initially the bit lines both will be, say, pre-charged, both will be at VDD, right? You pre-charge both the bit lines, you turn on the word line, and what is going to happen? Because either Q will be 0 or Q bar will be 0. Whichever is 0, that will discharge the bit line, right? Because before you start sensing operation, you will pre-charge both the bit line to high voltage, 1 volt. The moment you turn on the word line after that, one of the bit line will reduce voltage because there is a direct discharge path. Suppose this Q bar is 0, right? That means this transistor is on. So that means this bit line will discharge through N2. Because this is on, right? So depending on which state you are you in Q equal to 1 state or Q equal to 0 state, one of the bit line will start to burn. And this little differential voltage between these two bit line will be sensed by a sense amplifier. So the purpose of sense amplifier is to speed up the readout process, right? So that's why these two bit line will be connected to the input of a sense amplifier, which will always monitor what is the differential voltage, and correspondingly it will amplify it and will send out the data from the chip. So that's the operation, read. During write, what is going to happen? During write, can anyone tell me what you will do? How you will, suppose this is Q equal to 1 after power it up, but you want to write it 0. What you will do? How you can write 0 here if it is already turned on as Q equal to 1?
Put 0 on the bit line and 1 on the
Absolutely,
bit line.
absolutely. So you utilize those bit line. Because bit line will differentiate one cell to another cell, right? Every cell has this bit line pairs. So suppose it is 1 and I want to write is 0, so I'll put bit line 0. So whatever data you want to write, you put it on the bit line, right? So that is set the voltage of this bit line, and then when you turn it on, now this cell, right? Because it is 1, this cell will now get charged. This bit line is a highly capacitive, right? It's a big capacitor bit line you can think about, because it's a long metal line, bit line. It's a whole column, right? So that's why understanding this structure is important when you talked about here. So this is 1 bit line. So 1 bit line is a long line shared by many word lines. But you are looking at a particular cell now, right? So that bit line will come in, but that capacitance of this bit line will be significantly higher. That's why charging bit line will take a lot of time, a lot of energy, because it's a high capacitance, right? It also, so what is going to happen? So now you have charged this bit line. Now you turn this on. This capacitance, right? The cell capacitance, or effective capacitance at Q will be 10 times smaller, much smaller. So even if bit line loses few picocoulomb, right? Q will be fully charged. Because this bit line capacitor is much high, right? That means it holds a lot of charge. Small amount of charge will go to the Q, and that's how you flip the bit. Because if Q from 0 to 1, it goes, immediately it will go from 1 to 0. Because of this positive feedback. So that's the right operation. Okay, so you put the data on the bit line, turn on the word line, immediately the cell will flip. And if it is the same data, suppose this is Q equal to 1 and you also write 1, then nothing will happen actually. You turn on the device, but nothing will happen. Because this is already 1, this is also 1, so yeah. So let's see how you will write and overwrite on the cells. Any question here? Okay, so this is the thing I was talking about. So bit line, you can think about is a capacitor, large capacitor. The capacitance of the bit line will be nanofarad in that range, right? Both the bit lines you can think about is capacitance, and this storage node Q, you can think about another capacitance CQ. This is storage node capacitance, right? Those capacitance is a combination of say gate oxide capacitance, gate to drain capacitance, all the capacitances. Right, in a CMOS node, you can think about. This will be in femtofarad range. Femtofarad, right, 10 to the minus 15. Whereas this will be in, at least in nanofarad, or maybe in picofarad. So 3 orders of magnitude difference will be there. That means little bit change from here will completely charge this capacitor. Charge here means with respect to VDD. VDD is the voltage, maximum voltage in this cell. Whenever you charge a capacitor to VDD, that means it's fully charged. Okay, so we'll talk about some of those charge sharing calculations and all, that when this capacitor becomes fully charged, how much charge is lost from the bit line. We can easily calculate based on the capacitance values, and in your homework and all, you'll do that. And so that's how you can think as a conceptual model, right? So when Q equal to 1, that means this capacitor is at VDD, and Q equal to 0 means this capacitor is. So this is not a physical capacitor, this is a conceptual capacitor, right? In any CMOS circuit, every node has a capacitance corresponding to all the cells surrounding it. The source to drain, gate to source, right? Because this is connected to source of this transistor, it is connected to this source, right? So that those source to gate capacitance and all those things will come in. So yeah, you can think always conceptually this, there are 2 capacitor, which is a cell capacitor. Its value will be in femtofarad, as well as there is a bit line capacitor, which are in at least picofarad range. So 3 orders of magnitude, and when you charge those bit lines. So that's why this pre-charge is a expensive process. So there are a lot of patents, things goes on, how to minimize the time and other things. I mean, do we really need VDD? For this, in this particular 6 transistor case, yes, you need. But for there are many other design variants where you may minimize some of those excess times and all. But let's move on to, in terms of understanding the operation a little bit more, okay? Yeah. So let's look at the cell operation one by one, because we will be going a little deep into the operation of this cell, right? Write operation. Conceptually, we understand, okay, for write, we have to put bit line accordingly, whatever data I want to write, I want to put that data on the bit line. This is conceptual. Now, in terms of mathematics, equation and all, we'll go a little bit more as you go forward, right? So let's look at the write operation. This is the write operation. Your biasing point is, suppose I want to write, so in this particular case, what data I am writing? I'm writing 0, right? Because the data it is holding, so it is dependent on Q. Q is holding 1. I want to write 0, that's why I put bitline 0. So you look at here, this is the complementary part, bitline bar or Q bar. You set it 1, automatically it will be, other will be set, because this is a back-to-back inverter action. Okay, so it is holding 1, now I want to write 0. So I'll first precharge those bit line accordingly. So I'll precharge this bitline bar, I'll keep bit lines grounded, and then I turn on the word line. So this is the timing sequence. First precharge will happen, then turn on the word line will happen, then there will be a competition, and you will see that sometimes write can fail. Because the inverter, right, they don't want to change their state. This inverter wants to keep, it's a static RAM, they want to keep Q equal to 1. And which transistor we want to keep Q equal to 1? Out of 4, N1, P1, N2, P2, right? If you look at the structure. The PMOS transistor. The PMOS wants to keep it charged because PMOS is on. It wants to always charge it. The moment you lose some charge, PMOS will push more charge in. So that means if this bit line wants to discharge this node, but this PMOS will charge this node. So who has to be strong to win this race? Who has to be strong means this is one transistor. So maybe I can go back to, let's see. Yeah. So looks like here, right? So this is P1, PMOS, that wants to keep this Q equal to 1 because PMOS is turned on. And if you want to write, you put bit line 0, right? And this transistor, so every transistor has certain current carrying capability, which is the saturation current, right? In the first class we talked about. Every transistor has its maximum current capability based on overdrive voltage, based on whatever gate voltage you apply. Now, in order to make write successful, which transistor needs to be strong? Is this access transistor needs to be strong or this PMOS needs to be strong? And why? Access transistor needs to be strong. It has to drive more current than the PMOS because PMOS wants to keep it 1, right? That's the purpose of this PMOS. And this access transistor, now when it is on, it wants to discharge this node. So it needs to discharge at a much faster current or much higher current than the PMOS can charge this Q. And that's why you have to size them properly to make sure that write is successful. If you don't size them, if you size, suppose, let's ask this question. Suppose this access transistor and PMOS are sized equally, means W by L ratio, right? Which is the size of a transistor, are same, for example. Do you think write will take place? So both the transistors are sized equally. Now sizing is one factor of your current, right? If you recall your current equation. So I is mu Cox W by L is the size and V overdrive square, right? Vg minus Vd. That's the equation. I size both the transistors same. Now I want to flip this side. Question is, will it be possible to flip or I will size differently? No, what do you think? So if you size equally, right? So this mu will be different for NMOS versus PMOS. So PMOS is mu P or mu H, right? And NMOS, INMOS is mu N. Same, other things will be same, overdrive factor will be same. Okay? So mu N is typically 2 times higher than mu P. Electron mobility is high. So even if you size them same, in this particular case, still NMOS will win or access transistor will win. Right? So, okay, so that's the thing. the computation during write. And that sizing ratio is called pull-up ratio, is defined as, oops, sorry. So yeah, this is the process. I think, let me see if I missed anything. Yeah, so this is where we are. So this is the write operation. We'll talk about hold operation next, and then finally we'll finish the lecture with the read operation, okay? So let's look at the write. So this transistor is turned on, this bit line is 0. This P1 will compete with this NMOS N1, and that's how this Q has to be discharged to ground, right? When you discharge this Q to ground, then transistor will, or this SRAM cell will flip its state. Do you really need to discharge it to ground? Or what is the minimum value of Q should be to flip the cell? So Q right now is at 1 volt, right? I'm saying, yes, you can eventually Q equal to go to 0 volt. But what is the minimum voltage you need to bring down? After that, this back-to-back inverter will take care of it. Less than half is a good answer, but more conceptually, it is a threshold voltage. You have to turn on this NMOS, right? Or this PMOS. So you have to go to the threshold voltage level so that this PMOS turns on and it will charge this node. Okay, because this is at high. So this high voltage keeps this PMOS off. You need to turn on this PMOS. Okay? Or in other words, you need to say turn on this NMOS using this Q bar voltage, right? So whichever way you can think about. So the threshold voltage is the main, or more exact value will be the metastable point that I said, that crossing point B. So you have to bring the transistor voltage Q below this metastable point. After that, inverter will take its action. So metastable point is, that's why it's important. The butterfly curve, as you saw, that, yeah, so you have to bring down this voltage below the metastable point, and then inverter will take care of it. Okay, so that's the PMOS. PMOS action is to charge this capacitor on, and NMOS is to discharge to ground, and that's why there is a competition between these two transistors. Both are on, right? P1 will compete with excess transistors, let's call it them A1. And the ratio between PMOS sizing and NMOS sizing, NMOS excess sizing, is called pull-up ratio. So you want pull-up ratio should be high or low to make write smooth. So like multiple choice questions will be there, right, in midterm 1. So there's something similar can come. Pull-up ratio should be high for efficient write. Is it a correct statement or false statement? The false statement. Pull-up ratio should be low. Lower the pull-up ratio, more efficient is your write, because low pull-up ratio means excess transistor is more strong. Okay. Now, next question, like last year I asked, if pull-up ratio is less than 1, write will fail. Is it true statement or false statement? Pull-up ratio is less than 1.
So false.
False, not necessarily, right? Because PMOS has some weakness, right? It has less mobility. So NMOS has that added advantage. Its mobility is 2 times more than PMOS. So yeah, those are the things conceptually will be asked in questions in midterms. And there will not be any partial points, so you have to be careful, yes.
Sorry, could you repeat that? So
Yeah.
you said N is usually twice as large as you said H.
Yes.
And if the pull-up ratio is less than 1,
Yeah.
you asked the true or false question. The answer was false.
Yeah.
But how did?
So let's assume the pull-up ratio is 1. In that case, NMOS is twice strong than PMOS.
Okay.
So if pull-up ratio is 0.5, then yes, you cannot write.
Okay.
Then NMOS and PMOS will be equally strong, so you cannot discharge it.
Okay. That's,
So based on the mobility ratio, or more specifically the mobility ratio, pull-up ratio should be more than mobility ratio, which is 0.5, right? If you put PMOS mobility and NMOS mobility. Yeah, that's the thing. Yeah, these are good questions. Any question? I mean, if you ask questions, it gives me also time to explain it a little bit more. Yeah. Okay, so that's one important thing. So typically, pull-up ratio, you design it around 1.5. You keep margin, right? You don't want to keep on the edge that, okay, both NMOS and PMOS are equally strong. No, I want to make, you want to make advantage of this. One is this mobilities, also keep some margin. Okay, so this is the mobility is the one which makes mu h is half of mu electron, and that's what you need to think about in the pull-up ratio calculations. So we'll solve few problems, maybe next class we'll solve, and the homework 2 will be coming up, which will involve all those pull-up ratio, pull-down ratio calculations and all. Okay, now let's look at this timing. This is very important in memory because you want to read, right, in nanoseconds. 10 nanosecond, maybe, or 5 nanosecond, you want to read out the data. That's why this timing has to be highly optimized. So, and it also gives you this sequence of events happening during, say, write. So I want to write also in a couple of nanoseconds. So what is going to happen that these bit lines, right? Bit lines are charged. For example, you want to write 0, so you pull down this bit line. So bit line discharge to ground by write driver, because during read and ideal state you don't want to touch those bit line. During write only you pull it down, right? So says at your ideal state you put everything charged or everything ground, but here let's assume your ideal state is 1, bit line, both bit line and bit line bar is 1. The moment you want to write, that's that point onwards, you will discharge one of the bit line, other bit line will be same. Little glitch you see is because one bit line is going down, right? There will be some bit line to bit line capacitive coupling, but that's very little. This will cause, so bit line bar will remain at 1, bit line will go to 0 because you want to write 0, and then this action will take place. So this Q will now flip and Q bar will go up, okay? And this metastable point will decide, right, when to stop, right? So you can bring it down or you can turn off, for example, this word line much here, because by this time the cell has been flipped. So you can optimize some of those things. You don't need to fully wait. Yeah, you can do that if you have, if you're constrained as not. If you don't want to design ultra fast SRAM, then you can wait for things to settle down, but you can turn it off even a little bit earlier as well. But industry does that. That's why they have different grade of SRAM. If you just type in Amazon, there will be high-speed SRAM, ultra-stable SRAM, low-power SRAM, different types. It is all made of 6 transistors like this. But you just have to optimize your timing and other things based on that. Okay, so this is high node discharge. High node here is the Q equal to 1. So Q equal to 1 will discharge through pull up P1 and excess transistor. Excess transistor needs to be stronger than the pull up transistor, right? Because when this is 1, these two are on. So that's why there will be a competition between these two, and that's how Q1 will be discharged. Okay, so that's all about write operation, right? You know the equation of current. You can plug it in, and you can find what should be the pull-up ratio or pull to make sure that write happens, right? So we'll see a couple of those questions in the next class. Now let's look at the hold operation. The next important thing is the hold, and then finally we'll show the read operation of SRAM. So during hold, what happens is word line will never be turned on. Word line is 0. That means both the access transistors are off. Then whatever the SRAM content, SRAM will have some value. It will not be an indeterminate state. The moment you turn on your device, right, there has to be a state of the SRAM cell. It is not an undefined state. It will be 0 or 1 depending on the process variation. So it is there, but you are not turning it on the word line. And if you want to read the uninitialized content, then you just need to read without writing. Turn on the SRAM and read. Then you are knowing what is uninitialized content. If you want to write after that, you can write and that data will be there. And finally, we'll see how to read, right? That's another very important point. And there you will see competition between two other transistors. We saw competition between PMOS and access transistor during write. And we will see other way. Competition between two NMOS. One is the access transistor and the pull down transistor. That's what will happen during read. Okay, so let's look at the hold operation and then we'll go to read. So hold. So hold operation is completely determined by leakage, right? We talked about CMOS. Post-Dennard scaling is quite leaky. your leakage current is, I mean, if not nanoamps, at least picoamps range, right? So that's significant. But if your PMOS is turned on, so that's why normally leakage will not impact this cell state. But for optimizing the leakage or optimizing the power dissipation, you will not keep VDD at supply voltage when you're holding the state. You will lower down it. But I know that, okay, this bank of SRAM is, I don't need right now, but I want to keep the data on that. So I'll just lower it down to minimize the power dissipation. Because everything is power driven right now, right? Because post-Dennard scaling, power dissipation is the main design criteria. So you will pull down, you will operate the SRAM at a low voltage, which is called data retention voltage. Every SRAM will come with this voltage. You want a high data retention voltage or low data retention voltage for a good? Low, right? Because you want to retain data at say 0.1 volt or 0.2 volt, but maybe your technology will not allow it. And what decides that? This leakage. Because this leakage, more like subthreshold leakage, for example, think about this is the subthreshold leakage current. So it has a certain threshold voltage, every transistor, NMOS. NMOS here is the main culprit for leakage, right? Because this, either this Q equal to 1 or Q equal to 0, this, if Q equal to 1, this NMOS will leak it out and will try to minimize your retention. So if you, so by lowering the voltage, you are not changing the leakage current. See, in the leakage current, this threshold voltage driven. But by lowering the voltage, you are making PMOS weaker. Because PMOS overdrive voltage depends on whatever VDD you are operating, right? So overdrive voltage is what? Overdrive voltage is VDD, supply voltage minus VD. This is your overdrive voltage. You're lowering the supply voltage, you are making the transistor weaker. PMOS current will be low, so that means at some point NMOS will win and it will flip the cell. Leakage current will win at some point. So that will decide what is the minimum voltage you can hold the state. It can be 0.1 volt, 0.2 volt. And here you have to worry about the extreme cells because one bit flip, right? Think about your FPGA configuration. One bit flip in your FPGA configuration memory is SRAM. One bit flip will mess up your entire configuration memory, right? So you will be, so this is an extreme value problem, right? So there will be median cells which are good. So every median cell is a 0.1 volt. They can keep the data. But there are few cells, right? Maybe 0.001%, 1 out of 1 million. That can retain data maybe at 0.3, 0.4 volt only. So your data retention voltage will be defined by them. So that's the statistics, right? In industry, memory industry, when I was working, statistics was everything. You don't worry about median. Median will be always good. We always worry about the extreme cells. So this is one example. So your data retention voltage will be determined by these extreme cells, which has high leakage. Because of high leakage, they have high data retention voltage. Right, so that will decide what is your minimum hold voltage that you can have. So this is the leakage current, and you equate this leakage current with on current. And that's why you find out what is the data retention voltage. Make sense? Or so there will be problems. We'll be solving concrete problem. I am giving you equations and ideas how to approach them. Okay, so this is the competition. Yeah, this also will leak. This is not just N1 is not only one, because in the whole state, suppose bit lines are grounded, right? So then this bit line will also leak. Word line is also grounded, so there is gate leakage comes in. We talked about several leakage component, right? Subthreshold leakage will be this one, because here the leakage will be from drain to source. It's subthreshold because this transistor is off. Its gate voltage is below threshold, right? So this is the subthreshold leakage, but here it will be gate leakage, right? So all those leakage mechanism comes in. So this two transistor will add up, and you'll see whether this PMOS is strong enough to keep that cell to keep at Q equal to 1 volt. Okay, so low to leakage, or how to reduce leakage, sorry. Yeah, so how to reduce leakage? Of course, you have to either do threshold voltage engineering. I think in my leakage slide, you can see there are a few ways. With leakage is very much threshold voltage driven, specifically threshold and all. So next question is, suppose your nominal data retention voltage is 0.3 volt. Right? Nominal means at room temperature. If you go to high temperature, do you think data retention voltage will be high or low? Or will the same DRV voltage will be applicable at high temperature? Yes, so it will be higher, right? Because higher the temperature, more is the leakage. Look at this equation. Right, this temperature T will increase the leakage as you go to the high temperature. So at higher temperature, you need to keep your whole state at a higher voltage, which is again the lossy mechanism, right? The more high voltage you keep, power dissipation will be higher as well. So yeah, high temperature is bad for any leakage. Okay, so now this is the experimentally measured data on DRV on some technology node, maybe, I don't know, 90 or, yeah, I think in our group also we measure these voltages and all. If you want to choose your project on certain, say, 65 nanometer node, you want to measure DRV, I can train you guys, right? So project is quite open-ended depending on your interest, right? I'll of course share some papers as well, but this is one thing you can measure as well. If you like, I can give you all the ingredients. So x-axis is your data retention voltage, y-axis is the number of cells. As I said, median will be always good, but you don't worry about them, you worry about this upper tail. Where some of the cells here, right? Say 150, so then or 200. There are few cells which has 200 DRV. So your DRV for the chip should be 200. So that's the upper tail people worry about. And higher the density or lower the technology node, this upper tail is becoming more and more wide. And why this? So this is the conceptual picture of this data retention voltage. So this is your static noise margin, right? This butterfly diagram, and the highest square that you can fit in, that is the noise margin. Noise margin means, yes, you are at 1, but even if some noise comes in, right? And it will pull you here, but it will still go back here. So unless you cross this crossing point, you will be always, as long as you are staying it here, you will be eventually landing up at 1, even though there is some glitch which will lower the voltage, right? So there is a static noise margin. We want high static noise margin. That depends on what is the voltage you are operating in. But if you lower the voltage, your butterfly curve will be similar, but looking like this, RAD1. So RAD1 is when your SRAM operating voltage is say at 0.5. The blue one is when SRAM operating voltage is 1 volt, supply voltage, VDD is 1 volt. Then this is your butterfly diagram or static noise margin curve. When you're operating at a lower voltage, at 0.5, this square size is also low. That means little bit of noise can trip you off, right? So that's what happens in DRV. When you measure DRV, as you go down and down, little bit of noise will make the cell change its state. Or in other words, your SRAM is becoming more sensitive to noise. It is no more static anymore, right? Or it is no more stable cell. As you hold this data in a lower voltage, it will be more sensitive to environmental or thermal noise and other things. Okay. So let's talk finally the read operation. So let's see. Okay. So you want to read the content q equal to 1. This is your content, right? So how you will bias? What are the sequence? The cell is storing q equal to 1, and you want to read, right? Whether it is q equal to 1 or q equal to 0. The first thing is you put both the bit line, you charge them first, VDD, precharge your first step. Second step, you activate those word line. This is the second step, right? So bit lines are at VDD, so you can see the bitline capacitance VDD, and this bitline bar is also at VDD. But the moment you activate the word line, since this Q bar is 0, now this bitline will start to discharge. This will hold the data because in both sides, Q equal to 1 or high voltage. Make sense? This access transistor, this is also 1, this is also 1. So even though this access transistor is on, there is no current flow. Okay, but here, there will be current flow. And current will flow from bit line to the ground through this access transistor and NMOS. Now tell me which one needs to be strong. to read, because during read, right, this node can go to VDD as well, because this node is seeing VDD very close. So this bit line wants to charge this capacitor, because as I said, right, every cell is a capacitor. So this bit line wants to charge this capacitor, and if it gets charged, the cell will flip. So there is a chance that during reading, you upset the cell state. You don't want to upset the cell state, right? You want to keep the cell state when you are reading. Reading should not upset the stored value. But there is a chance, right? Because the moment you turn it on, this bit line being at high voltage will try to raise the voltage at Q bar. Do you see that? So now how to prevent that? How to prevent read disturb? This is called read disturb. During read, if you upset the content, it's called read disturb. How to minimize? How will size this transistor? Can anyone tell me which transistor will size bigger? Here mobility factor is gone because both has same mobility. N2 needs to be bigger, that's correct. Because you want to keep it at 0, so this has to be strong to pull it down to 0. This is called pull down transistor. So pull down transistor should be the strongest in the SRAM cell. Next will be XS and then will be PMOS. Yes? Yeah, both are identical. Because suppose you are here, we are talking about Q equal to 1, right? In some memory cell, it will be Q equal to 0. So which side is 0, right? That is where computation will take place. Yeah. Okay, so that's another consideration for SRAM transistor, and that ratio is called pull down ratio. And this is the waveform. Again, timing analysis is critical in memory operation, because that's how you optimize the time, latency. So here, your starting point is both the bit lines are pre-charged high, right? So this blue and red are basically bit line and bit line bar, both are pre-charged to high. And then you turn on the word line. The moment you turn on the word line, one of the bit line will discharge, right? And few millivolt is good enough, because there is a sense amplifier connected at the end, which will amplify the state, right? Before sense amplifier was invented, you can see sense amplifier invented was maybe 1980s. Before that, the SRAM was ultra slow, right? That's one of the reasons why the commercialization and all took place late, because in the absence of sense amplifier, you have to wait for so long for the bit line to discharge. But here, you don't need to wait. A little bit difference created between bit line and bit line bar, you amplify it and latch it out. So that's the purpose of a sense amplifier. Because these bit lines are heavy. Heavy means high capacitance. So little bit change will take longer time. Right? You'll solve few problems as well, quantify exactly how long it will take to discharge and all. So this is one thing you need to see, Q. So bit line bar will go down and word line is up. And here is the interesting thing. So this is very important parameter to understand. So during this read process, there is a chance that Q bar can flip, because Q bar is going from 0 to high voltage, and then again it will come back to 0. But if that high voltage is more than your metastable point, you will flip, right? So during read, you will disturb the cell. So how much high it will go, that is the important design parameter, right? During read operation, how much voltage will raise at the Q equal to 0 node. So you can calculate using equations and all, and we'll solve problems in the homework too. You will find how much high it will go, and will it be enough for disturbing the cell or not? We'll answer them. Okay. Any question here up to this point? Okay. So that's the read operation, and this is the comparison between two NMOS, access and pull down NMOS, and sorry, I think ratio between these two NMOS transistors is called pull down ratio. I think maybe in coming slides I'll show that, but so this pull down NMOS size divided by access NMOS size, that is the called pull down ratio. So you want pull down ratio should be high, so that NMOS can discharge, or NMOS can keep Q bar to 0. Okay. So I think read disturb is more severe, because you will be reading SRAM quite fast and significantly more for read intensive workload. So you don't want to upset the content. Okay, now in terms of speed up and latency, right? How long it will take to read. This is the equation you can use. So I said, right, bit line has to discharge for some voltage, say 50 millivolt, in order to sense amplifier to work, right? Sense amplifier also requires some threshold, some voltage drop between, or some voltage differential between two bit lines. So this, suppose it is 50 millivolt, then use this equation, bit line capacitance time this change in voltage divided by current. Current is your saturation current, for example, NMOS saturation current. That is the current through which bit line will discharge. And this equation will tell you what is the delay. You see how this equation comes in? So as I said right at the beginning of this course, if you know this equation, as far as you know, this Q equal to CV, right? This is a fundamental high school capacitor equation. Charge on a capacitor is capacitance and voltage. You are pretty much 80% of the course is done. So that's what we are using it here. Just so Q, I can write it as current times time, right? How much charge? And this is equal to capacitance times change in voltage. So change in time, change in voltage. So that's what it is. So delay, this is time. So I cell. Just see if we can put it down. So you will be using this equation in many ways. You can see. We'll come back and again. So you can answer what is the minimum time delay you need to sense the sense amplifier or to sense this content of the SRAM using this, and we'll solve the problem in the next class. So this is the read margin. So this Q will go from 0 to Vx, as I said, during the read process. And this Vx should be lower than the threshold voltage of the transistor. Because if it is more than threshold voltage, this Q will be on. Right now N1 is off because this is 0, right? Or this is Vx, which is lower than the threshold voltage of N1. The moment it goes to threshold voltage of N1, this will turn on the device. And if N1 turns on, this node will start to discharge as well. So this threshold voltage is very close to your metastable point as well, closer. They are all related, if not exactly. So exact answer is Vx should be lower than the metastable point. In an inverter butterfly curve or static noise margin curve, that metastable point is so significantly important, right? You want to be at symmetric, otherwise either reading 0 will be problematic or reading 1 will be problematic, right? So so this Vx is an important parameter and we'll characterize it. Characterize means we will find equation that what will be the Vx or maximum value of it during the read operation with some problems in the next class. Okay, so now techniques to improve noise margin. One is, of course, you can design SRAMs with high VT transistors. With high VT transistor, you can improve this noise margin curve. Right, so if you look at the diagram, this is definitely a better noise margin because you can fit in a bigger square. You can fit in very small square. That means here noise margin is less. So that means it can flip, right? One of the transistor can flip and then you can go to a low state. So read should not be destructive. SRAM read should not affect the stored value. You can read any amount of time. For DRAM, for example, read is a destructive read. When you talk about DRAM read, after read, you have to write it back. Otherwise, when you read, data is gone. But in SRAM, it is not like that. That's why it is faster and more energy efficient. Okay, so this is the one I want to say. This is called pull-down ratio or beta ratio, right? So it is this NMOS, pull-down NMOS in the numerator. So either pull-up NMOS or pull-down NMOS will be the numerator. Denominator is always excess in those ratios, right? So that's how you can remember it. And beta ratio or this pull-down ratio and this Vx are highly related. So right, so if you design the transistor with high beta ratio, like 2 or 3, so y-axis is your voltage rise, this Vx fellow. So Vx will go down as you design this NMOS stronger and stronger, right? And that can be easily derived as well with, if you plug in the equation of those transistors, you will see how to derive that number as well. Okay, but in general, this is the plot. Cell ratio, which is nothing but pull down ratio, should be high, because here mobility will not help you, because both they have same mobility. So you have to have at least more than 1, like at least 1.2 is to give some margin. Make sense to all of you? Okay. Questions, anything? I see a little bit silent so far. Make sense or? Okay. So now let's quickly, I think I have a few more 10-15 slides. I'll little bit speed up. So techniques to improve the read margin. One is, of course, you can have high supply voltage, right? You can operate the transistor at high voltage, then of course your noise margins and all will be high. Or you can think in this cell itself, right? You can have a slightly higher voltage. Suppose your global supply voltage is, say, 1 volt. But to keep the cell, right, instead of lowering the supply voltage, you can read or write at a higher voltage, say 1.5 volt, and during hold, I'll keep it low. You can do all those tricks to improve the read noise margin. And read noise margin is a serious issue because there is a competition between both NMOS, and it can flip the bit. Okay, and you can characterize using this butterfly curve and see is your noise margin is high enough to retain the data during read. So if you use transistor with low VT, your noise margin is poor. If you use high VT transistor, as you can see, these are all experimentally measured data. Its noise margin improves because high VT transistors in many ways are good in terms of leakage. It is good in terms of but high VT transistors problem is because overdrive voltage will be low. If you increase the threshold voltage of the transistor, your overdrive will be low. So that's where I think you cannot make more than 0.5 because supply voltage is 1 volt already. Okay, so let's summarize. So we talked about 2 important constraints. For good writability, pull-up ratio, you have to design in such a way that access transistor wins. Because access transistor will decide whether write will take place or not, right? Because PMOS will always oppose the write operation, and that is given by this pull-up ratio constraint. During read, you want access transistor to lose, right? Access transistor should not flip the state. So beta ratio should be high, right? As high as possible. Definitely more than 1. Okay, so that's how we can design. And any question on SRAM cell sizing? Okay. So now let's solve one problem, and before we go, so this is not the one. Yeah, so let's think about this problem. This is one of my research topic. Right now, my group has a lot of funded research on SRAM, using SRAM for different purposes, like for space, for example, you think, right? You will be using SRAM in satellites, in CubeSats. So there, one issue is this radiation effect, soft error, that anytime a high energy particle goes through it, right? It can flip the bit. Because if this, anytime high energy particle goes through it, it will deposit charge. And this charge will flip this Q equal to 1 to 0. And you can find out, you can see that this cell has been flipped. And so how to design, for example, SRAM for space, or how to design red hard cache memories and all. That's a important topic, specifically when space data centers are coming up, right? You know, right? There is a lot of push now to have data center in space for different energy efficient application because of free cooling, or at least efficient cooling. More than that, I'll say space is getting crowded because a lot of satellites are being launched, right? If you look at 10 years ago and now, there'll be significant difference in number of satellites which are orbiting in this space. So if for every communication, if you want to talk with the ground station, it is a huge loss in bandwidth. So if you have a data center in space, many of the in situ computation, right, can be done in space. So there are many reasons why there's a push for space-based data center, and that will have to solve or have to deal with this kind of issues on radiation effects and all. But this is an interesting question I want to ask before we're done today. Can we make volatile SRAM non-volatile? What does this mean? SRAM is volatile, right? You write data, you turn it off, power, you think data is gone. The question is, do you see any idea after today's class? Can you make SRAM non-volatile? Or what you will be using it, or what factor you will be using to make it non-volatile? Right, so. Non-volatile means every time you power it up, it should go to the same information. That means you have to play with the power up state, or you have to engineer the power up state. Right? So if you engineer the power up state, suppose, yes, process variation is not controllable, but during fab you can design. You can make preferentially one inverter stronger than the other during fab. And then that content will be always there. The moment you power it up, it will go to a known state. If not in fab, then during operation also you can do that. You can cause a lot of aging effect, right? CMOS aging is a interesting subject. So you can age. So you see, right, when it is holding, say, Q equal to 1, right? So suppose you're holding a data. And then this PMOS is on, this is off. That means this PMOS will age faster. So if you hold the data for long enough time, specifically at a higher temperature, you age it faster. So you can age so that you make one transistor weak, another transistor strong, and that's how you imprint the data you want to see every time you power it on. So there are many ways. One research approach we do is using X-ray, because if you turn it on and put it under X-ray, then X-ray will deposit a lot of charge. Whichever transistor is on, that will be affected by X-rays. Whichever transistor is off, that will not. So you change the threshold voltage and all through X-rays, yes?
Does that truly count as non-volatile since it will revert to its original state rather than maintain what was previously written?
It's a good question. So you're saying it is still volatile memory, but what I'm saying is you can use it as a read-only memory, ROM, which is the power up state. So it is serving two dual purposes. The same hardware, you can use it for read-only type of memory using the power up state, because power up state, if you engineer it properly, it will be always there. Anytime you need to read, just power it up and read the uninitialized value. You can also, but it will be acting like a volatile memory only. Anytime you want to write, you write it. But if you want to know what is the non-volatile component, it is just you to power it up. Yeah. Okay, so there are techniques to do that. And if you're interested in this topic, I can share some of my papers and other papers as well on this. So the key to answer is you have to understand this power up process. So this is the power up process. That's why I put these slides. When VDD is ground, right? So starting point is VDD ground. Everything is turned off. Both the node Q and Q bar, both are at 0. There is no power. Right? Even though it is inverter logic, you may think, okay, if Q equal to 0, Q bar has to be 1, but there is no power, right? So these both will be 0. So at the beginning phase, both the PMOS will be on. The moment you turn on the supply, both the PMOS will be on, because for PMOS to be on, its ground or its gate voltage should be 0. Both the NMOS is off. Now what is going to happen, that the moment you turn on the power, both the PMOS will charge their corresponding capacitances. And whichever PMOS is stronger will win the race. So that's what. So this is what exactly this simulation. You can do SPICE simulation in Cadence softwares, and you can easily do this. See, both the node, both Q and Q bar will increase with time equally, but one of them will slightly get ahead, and that will win the race eventually, and which will force the other one to go down. And that is your static point, stable point. But yeah, at the beginning, right, initial phase, there is a competition, and that's why little bit mismatch, very small, tiny amount of mismatch between the two PMOS actually decides what is the power of state. And if you can preferentially age, for example, you hold Q equal to 1, then P1 will age. If you hold Q equal to 0, then P2 will age. You can change this power of state actually. It is not like fundamental. So you can change the threshold voltage of the transistor by preferentially aging, or put your data on, then one will be on, another is off, and then put radiation and other things to cause preferential difference between these two transistors to imprint the content. Question, yes?
If you do that a lot, then it would wear out the whole SRAM faster, right?
Yeah, so this little bit is good enough to, yeah, you're right. You cannot do, then your noise margin and everything will start to suffer at some point. Yeah, you're right. We did some of those experiments. We find the DRV specifically, the data retention voltage, that becomes higher if you do this imprinting. Yeah, that's a good question. Yes?
And then what sort of impact would the time at which some program is storing memory during operation impact the
Yeah, it may, I mean, depends on the temperature. If you're at room temperature, it will take lot of time, maybe months.
Okay.
But you can increase the temperature, right? You put things in an oven, for example. My students, they do all the time oven. They put SRAM in 120C or 150C, and then imprint will be much faster within a couple of hours.
You heat one more.
Heat the entire memory chip.
Oh, okay.
Yeah. Okay, so that's an interesting topic. Still, there is a lot of things can be done. And yeah, for example, every chip should have a unique ID, right? That nobody should be changed or something like that also you can do, because power of state is used as a fingerprint of a chip, which is a process variation. But what we are doing is more like changing it for some useful purposes. For example, read-only memory, right? Which will be very, very tolerant to other variations and all. Okay, so I will stop this discussion here, but I'll leave these questions. We still have 5 more minutes, so we'll answer these questions and then we'll be done. This is, I think, one of the questions asked in the last year. Is this writing visible for everybody? Okay, so this has 6 transistor SRAM sized to operate as a stable cell in nominal operating condition. So it's both the bit lines should be pre-charged, which is whatever we learned today in class, right? Let's analyze the effect of peripheral signals on the SRAM operation. A, how does increased word line voltage affect the read stability of the cell? So, yes, so read stability. So word line voltage, right? Suppose you used to read earlier at 1 volt, now you're reading at 2 volt. That's what this question is. If you increase the word line voltage during read, right? How does increased word line voltage affect read stability? So will read be more stable or will be less stable if you increase the word line voltage? Read stability will increase. Oh no, sorry, it will decrease. Read stability will decrease because you are making this transistor strong, right? So overdrive, right? Overdrive is the main important thing, right, for transistor current. The current I is mu C ox and W by L V overdrive square. And what is overdrive voltage? V overdrive is VDD minus threshold voltage. Right, that's in a simple sense. So if you increase VDD, so VDD means not this VDD. This word line is only driving with higher voltage. This VDD is at 1 volt. You are driving word line at 2 volt. Then this transistor is becoming more strong. But for read stability, this transistor has to be strong. So since you are not changing this supply voltage, this is exactly operating at its nominal drive current, but it has become strong. That means your read stability will go down. So you're right. So this kind of multiple choice question can come, right, out of, say, B. What do you think? How does increased word line voltage affect read access time of the cell? Can you access the cell faster, slower? Faster. Because now your discharge current, right? I showed this equation, I cell will be high. What is I cell? I cell is the current through the access transistor. Okay, so you see, if you understand the concepts, you can answer this kind of conceptual question. So in midterm 1, which will be set to, I think, March 3rd, I'll make an announcement. So this is the way you will be tested, for example. How does increased wordline voltage affect the writability of the cell? Will it be more writable? Write stability will increase, right? Because wordline voltage will make this access transistor strong, and that is what you need for writing. You need a stronger access transistor. How does shortened wordline pulse affect read stability of the cell? More stable. Because the more longer you keep wordline on, this tripping point, right? This trip can take place. How does lengthened wordline pulse affect the writability of the cell? Let's see. Yeah, I'll come back to this. How does increased cell supply voltage means this one. So this is, so your nominal voltage is 1 volt, everything bit line, word line, they will be all operating at 1 volt. VDD, you are increasing to 1.2 volt, 1.3 volt, suppose. How does increased cell supply voltage without changing other signal affect writability of the cell? Yeah, so this word line voltage will make this PMOS stronger, so it will affect in negative way, right? It will be, so this is the conceptual thing. Let's see what is E, right? So this is the increased word line voltage will make A2 stronger. This is for A, B. Shortened word line pulse will improve the read stability as it reduces the total current drawn from the SRAM cell. Yeah, so you get less time to shrink, and this one, lengthen, will improve the writability as it gives the access transistor more time to pull the return side of the SRAM cell enough to flip the cell. Yeah, it gives more time to discharge. Yeah, okay, so these are the few conceptual things, and we didn't show much numerical problems, but in homework 2 there will be numerical problem solving questions. Maybe in the next class, I'm not sure, maybe I'll skip next class, but I'll make this announcement at least a day ahead. I'll let you know if I cannot make it, but the homework will be posted. So if I miss next class, we'll delay the homework submission a little bit more, but we'll have a complete homework on SRAM coming up. Okay, thank you.
Yeah, that's
I'm gonna get the
And I'll see you.
I'll find out once.
Depending on homework in the video.
What's up? Was it interesting? How's it been, lecture? That's gonna be huge. It's hard to understand. I know. Thank you. I got more of this lecture. Yeah, me too. See y'all. Wait for this.
Start for you now.
Yeah. Because that's what this class.
The questions put up on the board went on that bad. Probably most of them, right? Or like the ones that covered.